Welcome, everybody that's already joined us. We'll give it another 1 minute and then we'll get started. Still see people coming in. Okay, my clock shows 11:02 and we'll go ahead and get started. So, welcome. So this is OPGW Engineering 301. Today we're going to be talking about fault current in detail. I'm Mike Riddle. I'm president and general manager of InCab America. And I'll start off by noting the fact that this is a registered continuing education program compliant webinar. So that means that we've met their standards and you can earn an hour of continuing education credit through them. And we'll explain how to do that at the end of the presentation. But the fact that we're compliant does not mean that they are endorsing any of this content. So the purpose statement of today's webinar is, again, this is OPGW Engineering 301, Principles and Application of Fault Current. And we're going to talk about what fault current is, what fault current capacity is, how to calculate the required fault current capacity for a transmission line, how to calculate the capacity of a cable. Well, for both of these, we'll have a detailed discussion about the key variables and the methodologies that are used. We'll also talk about fault current capacity uncertainty and the pitfall presented by traditional ground wires. And we'll close out with looking at some possible solutions to fault current capacity challenges. Here are the specific learning objectives. I'll give you a minute to review them, but they're pretty consistent with the course purpose. See a typo at number 7. Somehow I missed that. Oh well, sorry about that. Okay, webinar rules. So we've already done the introduction, and if you're hearing me, then we've completed our sound check. Presentation is going to take about 60 minutes, and then after that, we'll be open for questions, which you can submit using the chat function, or we might be able to figure out how to unmute your mic so that you could just ask a question. We'll figure it out when we get there. During question and answers, they should be on topic. We don't want to talk about business. And today I just want to comment on something. A couple weeks ago, I had the COVID for the second time, not nearly as bad as the first time, I'll note, but I do have a lingering cough from it. So if I break down into a coughing fit, I apologize in advance, and I may be coughing here and there through the presentation. Sorry about that. So without further ado, so I want to orient everybody, hearkening back to the OPGW Engineering 101 presentation. So basically, this presentation does assume you have some basic familiarity with OPGW, whether you actually attended Engineering 101 or not. So it kind of assumes that there's a baseline of knowledge there. But to Remind you, the primary function of OPGW is to be a shield wire or a ground wire for a transmission line, and a traditional shield wire or ground wire actually had two purposes or two functions as part of that primary function. One was to protect the phase conductors from lightning, and then the second was to provide a path for fault current, and this is what we're talking about today. The secondary function, in quote marks, for the cable was housing optical fiber for data and communications. And like lots of things in life, what starts off as a secondary function in this day and age, in some ways, is actually the more like the primary function. People are more concerned about what the fibers are and how many there are and what they do than the original primary function. And throughout this presentation, and in fact, throughout our industry, shield wire and ground wire are used synonymously. So if I say shield wire, it's the same cable. I'm emphasizing, though, the protection from lightning. But if I talk about ground wire, again, same cable, but I'm emphasizing the fault current path function of the cable. But they really mean the same thing. So back in that OPGW Engineering 101 presentation, there's a slide with a lot in it. And because that presentation is talking about cable design principles, this comes towards the end and don't have a lot of time to go into detail in all of this. But basically, we do talk about that there's a utility side of the fault current issue, and there's a manufacturer's side of that issue. Well, today, we're going to do a deep dive into all of this. So to begin with, let's start at the beginning. When you think of a transmission line, most people, and civil structural engineers in particular, they see something like what you see here in the picture. But to an electrical engineer, and I'm an electrical engineer by training, by the way, we see something like this circuit diagram. So in a circuit, there's always a source and a load. And then in between, you have resistance and inductance and even some capacitance. But the point is that you have power starting at the source, and the current and the power flow through the circuit to get to the load. In a transmission line, the source is a substation bus or a generator, but then really generators aren't connected directly to transmission lines. They too are generally connected through another bus. So really it's a bus. And the load could be another substation bus. So you've gone from a transmission substation to maybe a distribution substation, and there's a bus there. But that bus is feeding ultimately a load that is comprised of our homes, our businesses, and other entities that are using electricity. And the big point is that you want that power to get to your load. So what's the fault? Well, a fault is just another word for a short circuit. Again, they're used interchangeably or synonymously. And again, you can make a distinction between how most people understand it and how an electrical engineer would look at it. So to most people, a short is just an electrical connection between two parts of a transmission line or a circuit that you don't want to be there. I mean, it's that simple. You don't want it there because it's not serving your purposes. To an electrical engineer, the definition is a little bit more, an abnormal condition in the line or a circuit where the current flows through an unintended lower resistance pathway instead of following the line or the circuit. And so that looks something like this. So we've still got our source and we've got our load, but we have this short or fault somewhere in between. It's a lower resistance pathway, so the current tends to bypass all of this other resistance and inductance and capacitance and whatnot. It bypasses that and goes from here to here. And as a consequence, the power doesn't get to our load, and that's bad. But we need to understand, we'll see why later, but you need to understand that the current doesn't just sort of disappear To an electrical engineer, what's going on is the the current always has to go back to the source to complete the circuit, but it's going through that lower resistance pathway, which means it's been greatly increased. On a transmission line, what that ends up looking like is in this picture. So in this picture, you see that there's an arc going from one of the phase conductors to the structure. So that's your short or your fault. Once the current gets to the structure, it's flowing through the structure and it divides. Some of it goes up to our shield wire, which could be a conventional shield wire, a 3/8 inch EHS, or it could be an OPGW, but it's going up to go through the shield wire or ground wire, whatever it is. But some of it is also going down through the structure and then flowing back to the source through the earth. But the point is that all of that energy has to go back to the source in order to complete the circuit. So in the real world, what actually causes faults? Well, contact with one of the phase conductors. So like a tree limb can come into contact with a phase conductor and cause a short. An insulator failure, which could be an electrical failure, so tracking. So the insulator, its insulation has broken down and isn't functioning properly anymore. Or you could have mechanical failure. So the hardware fittings of the insulator could break, and the insulator physically pulls apart. That can cause a fault. A conductor can break, or a conductor splice can break. A structure can completely fall over. There are lots of pictures on the internet of that, particularly during bad storms. You have structures fall over. And there are lots of other possibilities. Lightning strikes can induce an arc flashover. So in any case, there are many more possibilities up to and including a kid's bouncy house. So you set up a bouncy house near a transmission line. When there are high winds and you don't properly secure it, you can get a fault from a kid's bouncy house. Or here's another possibility. I'll note that the pilot did survive this. So although there are many causes, for our purposes, there are only two classifications. There's a single phase fault that would include the ones that we looked at, the contact with a tree limb or an insulator failure or a conductor / splice failure. Those tend to be single phase faults. A three-phase fault is the structure failure that I mentioned. The bouncy houses and the airplanes, they could be either depending upon how many phases they're affecting. And yes, there are other types, but these two give us the best case and worst cases to look at, and we'll understand why that's important in our topic today real darn soon. So now that we know what can cause a fault and what the classifications of fault are, then we can start to look at their key characteristics. And what we see is that there are two things that we need to understand and look at. The first is the current. We'll express that in kiloamperes, and we'll use the symbol I for that. The second is the time or the duration of the fault, and that's going to be expressed in seconds and with the variable T. We can use these to calculate the total energy flow, which we'll describe as the required fault current capacity. And the equation that we'll use is current squared times time. So I squared T, and the unit that falls out of this is kiloamperes squared seconds, Ka squared seconds. And this is sort of like an electrical equivalent to kinetic energy, kind of, sort of. Helpful way to look at it. So now we're back to that slide from our Engineering 101 presentation. We have a utility side, which is where we're calculating the required fault current capacity. And then we have this manufacturer's side that we'll get to later. For now, what we want to do is move on to understand what data we need to calculate the required fault current capacity. And first, we need that current. So recall that we had the two classifications for fault, the single phase and the three phase. So which do you use? And the answer is it's up to you. Because the decision of which that you use is really a risk management decision or a design philosophy decision. So consider these observations. So single phase faults are uncommon. Now that's my qualitative characterization. Somebody could come and say, well, there's a single phase fault somewhere in the United States every day. And maybe that's true. But even if that's true, compared to the thousands, tens of thousands of miles really of transmission lines around the country, it's still uncommon. And three phase faults are very rare in comparison to single phase faults. Both do happen, so you can't just ignore them. But what you can say is that I can make a financial argument that it is more economical long term to compute the required fault current capacity using the single phase fault current. But I can then make an engineering argument that reliability is better assured by using the three phase fault current. So which is more important to you? Is the reliability more important, or is the long-term finances more important? So again, it's a risk management type decision, not a technical decision. What's more important to you, the money or the reliability? So it really boils down to a question: how much risk do you want to take? Now, utilities tend to be conservative, so most do use that three-phase fault current. And I myself am an engineer, and at one point in my career, I worked at a utility, so I would use the three-phase fault current. But nevertheless, there are some utilities that do use the single-phase fault current because, as was said, you can make a financial case. It is a rational decision to do so. So just to underscore this point, which value you use is up to you. It is not your OPGW supplier's decision. Strictly speaking, your supplier should not care. Now I care because I'm just, a really caring person, but strictly speaking, they should, it's your decision, not theirs. So where do you actually get those values from? Well, you get them from the system planning department. They use special software to compute the values. It is not within the scope of today's webinar to actually discuss the calculation itself. It's just kind of, let's take that as a given for today, that they can calculate that. And I'll just comment that we're going to see that system planning department is really important throughout this presentation. You're going to need information from them. So it may be career enhancing for you to be nice to them. We will see later, though, that they're going to need some information from you. And so probably in your mind, you're thinking, okay, but what's the difference between the two? And what's the consequence of the difference between the two? So, specifically, is three-phase fault current 3 times the single phase value? Well, it turns out, for reasons we don't have time to go into, that no, it's not 3 times, it's around 2. For today, we'll just take it as 2. But let's go back to understand the consequences of it, or the ramifications of it, by looking at our fault current capacity equation again. It's I squared T. So this square here means that any current differential will be amplified. So that's better explained and illustrated with an example. So let's just say the single phase current for a line was 10 kA. I squared becomes 100. If the three-phase current was exactly twice that, 20 kA, that becomes 400 kA squared. So you've increased your required fault current capacity by a factor of 4. And to understand the consequence of that, The higher the required fault current capacity, the more metal must be in the cable. Must be, must be, must be. It is just plain physics. And more metal leads to larger cable diameters, which then in turn, higher weight goes with that as well, which means the two taken together means greater structure loadings, which means your structures can cost more. The cable itself will cost more, the hardware could cost more, and there are other consequences potentially beyond that as well. So that's why it's important that you be judicious in selecting the value that you're going to use. So we've talked about the current. Let's move on and we'll talk about the duration of the fault. And I'm warning you here that you're going to get more of this design philosophy as we continue on. So the duration is going to be the expected time the protective relay system will take to clear the fault. So how long will it take to trip out the line? And as with the current, we got multiple possibilities. For the duration, we're going to talk about 3. First up, a single contingency. So let's assume the line trips out and that's it. That's typically going to take 4 to 6 cycles. You can convert that to seconds. And I will note here that I'm doing all of these conversions using the US frequency, which is 60 Hertz. For those of the international audience, it could be 50 Hertz. You would just adjust accordingly. Basic concept still applies. So this contingency is the highest risk because most systems, and in fact, every single one that I've ever looked at, make at least one attempt at a reclose. And so what's going to happen if there's a reclose is that you'll have another 1 or 2 cycles between the initial trip and that reclose attempt. The cable cannot cool during that time. So effectively, you can't ignore this time differential. Then you have a second trip if whatever initiated the fault is still there, like a conductor failure. So in that situation, you've got 4 to 6 cycles. You've got that intervening period that you can ignore, whatever time it is. And then another 4 to 6 cycles. So for purposes of calculating fault current capacity, you can sum these together for a grand total of 8 to 12 cycles. And this is what I'm calling the double contingency. The third contingency that we're going to look at is basically what happens if a breaker fails. So in that situation, you get backup system protection, and that typically takes 22 to 30 cycles. Now, this becomes the most conservative, but like we talked about, single phase faults are uncommon, phase faults are very rare. Single contingencies, when it happens, yes, that's definitely going to happen. Double is very likely. Backup system failure is rare, but again, it does happen. So which do you use? Well, it's up to you because we're back to another case of risk management or design philosophy. You can again make a financial case for using the single contingency scenario. You can make a reliability case for using the backup system scenario. You can split the difference by using that double contingency. And for all I know, maybe your utility, there's 2 attempts at a reclose. And supplier, up to you. Excuse me. Yeah, up to you, not up to the OPGW. I'm pausing because I saw a note that it looks like I got dropped. Is everything okay?
It did freeze for a little bit, but it seems fine now.
Okay, good. Where did it freeze at?
You might just have to redo this slide.
Okay, I'll redo this slide. Okay, so which scenario, so back here, which of these clearing time scenarios do you use? It's up to you because again, like with the current, we can make a financial case for using the single contingency scenario. We can make a reliability case for using the backup system scenario. Or you could even split the difference and use the double contingency. And I think I mentioned that if your utility actually allows 2 attempts at a reclose, you could even come up with a triple contingency. So what you use is back in the category of it's up to you, and it's a function of how much risk are you willing to take. As with the current, most utilities are conservative and they use the backup system scenario. I do know of one American utility that uses single contingency, and I know of a handful that use the double contingency. So where do you get the actual durations from? Well, it's back to the system planning department. And I'll just comment that the clearing times that have shown in this presentation are what I've seen. So your system could be different. Your system planning department will have the actual value for your systems. And I also commented on this earlier. I converted using 60 hertz, but same concept applies. You would just convert using 50 hertz if that's what your utility is using. Okay, so now we've got the current and we've got the time, and now we're ready to do some math. So 2 examples. First example, the single phase current is 10 kA, and we're using single contingency clearing of 6 cycles, and again, assuming 60 hertz. So we get the required fault current capacity equals 10 squared times 0.1 equals 10 kA squared seconds. Example number 2, the 3-phase current is 20 kiloamps. We're allowing for backup system clearing, which is 30 cycles to keep the math easy. So we get a required fault current capacity of 20 squared times 0.5 equals 200 kA squared seconds. So you've gotten a big difference here. Typically, here at NCAB, we see values in terms of required values from utilities in the range of 50 to 150. A few lower, some higher. Huh. Somehow I lost my own slide. So I had added a slide after this slide. An important point about this is that the higher the required fault current value, the more metal you have to have. Oh, I did talk about that earlier. Okay, never mind. All right, so we've learned how to calculate the required fault current capacity, and we can move on to how the cable designer works with that capacity to come up with a rating for a particular cable design. So the concept is simple. We've determined what our required fault current capacity is, and we want a cable fault current capacity that is greater than or equal to what's been required. Easy peasy. So to compute the cable's capacity, we got to have our own equation, just like we had for the required capacity. And we've got to have the data that go into that equation, similar to what we did for the required capacity. So let's look at those. Plus, we ought to have a third, and that is that a utility should be having all of its cable suppliers use the same equation and the same type of data. Otherwise, you can't compare apples to apples design from different suppliers. So let's get into this in detail. The equation. So the industry standard equation or methodology comes from the IEEE standard 738. The 2012 version is the current one. At part 4.4.2, at equation 2b, you have a non-steady state heat balance equation, and it's this. Now, I want to take a moment, just a couple seconds, to ponder the beauty of this math. But let's remain calm. So we don't have to unpack all of this equation. We don't have the time for it anyway. I just need for you to understand that this is the general equation to describe a step increase in current. Note that. Um, but if you look at it closely, it's the change in temperature with respect to the change in time. Not exactly what we're looking for. In the Southwire Overhead Conductor Manual, just so you don't have to work it out and apply it yourself, reference the second edition. You can find at part 3.2.5, equation 317, they've taken the equation and specifically applied it to fault current rating. So let's look at that. Looks like this. I squared T equals A squared K log blah, blah, blah. Now, some of you are thinking, hey, wait a minute, this isn't any easier than the previous one to understand. And I'll just respond that I didn't claim it would be easier. I just said it would be applied. We're going to see in just a moment why that's important. Here we go. This I squared T is the equation that we already know. It's what we use to calculate the required fault current capacity. So that's easy, and it tells us that we're on the right track. This A squared is just the area of the cable squared. That's easy, just get it from a supplier's data sheet. Now the K is a value that's computed from the materials used in OPGW in the Southwire book at its equation 3-16, how you calculate K. Those materials are aluminum, aluminum clad steel wire, and aluminum alloy wire. And the type of data that you need is basic data, density, specific heat, resistivity, and all of that data is relatively available. It's right there in the book too. So that's easy. That just leaves the T's and the lambdas. So the lambdas are the inferred temperature of zero resistance. Now that sounds esoteric and or intimidating, but the values that we need are there in the book at a particular table. So it's also easy actually. So now we only need to think about the temperature. Those temperatures are very important to the outcome of this equation. The T1 is your initial cable temperature before the fault, what you assume the cable is at before the fault current condition. That is not the air or ambient temperature because a cable is going to absorb solar radiation, and so it's often hotter than the air around it. Obviously, at night, it may be the same as the air around it, but on a hot summer day, it's going to be hotter than the air around it, just like your car gets hot when you're parked outside on a sunny day. The T2 is your final temperature, so it's the highest temperature that you're going to allow the cable to experience. These two variables are going to have a huge influence on the outcome of this equation. And we're back to the same question that we keep having over and over again. What values do you use? Well, for T1, for a long time, the de facto industry practice was to use 40 degrees C, which is 104 F. It's a realistic cable temperature on a hot summer day. That's reasonably conservative and it's widely applicable. But it is appropriate to adjust up or down based upon your local climate conditions, right? So I gave this talk years ago to a utility in Maine, and they decided that they have their high temperature during the summer is maybe 90 degrees for 3 days in July. So they decided to just use 35 degrees C. I was fine with that because this is another thing that's in the category of to the OPGW supplier, what you choose to use is up to you and they should be indifferent to it. On the other hand, today in Texas, like we've had, I don't know, I've lost count, 20 straight days of the temperature over 100. Yesterday it was 106, so slightly above this, which means a cable would have been much hotter than 40 degrees C. Today we're having a bit of a cool spell. It's only going to be about 100. So what's that, about 38 C? So West Texas, they might want to use 45, or you could maybe even make an argument of using 50. But again, what you use is really up to you. Cable suppliers should be indifferent to it, but you do need to make sure that all the cable suppliers use the same values. I will comment before moving on that, in my opinion, it is not at all appropriate to use 20 degrees C, which is 68 degrees F. I see offshore suppliers, meaning suppliers outside the United States, using that all the time as T1. That's a rough average ambient air temperature in most of the world. It has nothing to do with what the cable temperature is going to be, especially not if you assume a hot summer day, reasonably hot. What about T2? Well, what had been generally used is 210 degrees C. Now, this had crept up. When I first started working with OPGW, everybody used 180, and then it became 200, and then it ended up at 210. And that's a reasonable, safe final temperature for any OPGW design. The reason for this is that above that, the optical unit could be damaged. It doesn't matter what type of cable it is. In an aluminum pipe type design, you've got plastic buffer tubes with gel, and the tubes and or the gel could begin to get damaged by that much heat. In designs with stainless steel loose tubes, whether center tube or stranded, the gel inside begins to come into risk. Incidentally, the fiber itself, for a short exposure, no problem. So it's other components, though, of the optical unit that you have to worry about. And in addition, somewhere above this, you begin to lose strength in your aluminum alloy wires. They're heat treated, which gives them some of their strength, and you begin to lose that. They don't contribute a lot, but they are contributing. And there's nothing good that can come from turning them into just dead weight. And specifically, you would be increasing the cable sag greater than what was designed. So you are creating the potential for clearance problems. Why take that risk? So another comment is that final temperature should apply to the hottest part of the cable. This is just for rules keeping purposes. We'll explain why in just one moment. It turns out that the current is not going to be evenly distributed within the cable. Your aluminum alloy wires are going to tend to heat up the most, and your optical unit is going to tend to heat up the least. And the difference you can get between the two can easily be 30 degrees C. So if supplier A is using this definition and another supplier is defining it as the coolest part of the cable, meaning the optical unit, that becomes effectively a way to cheat. So they're hiding what is really a higher final limit. So let's recap. So we've now got an equation and a methodology for computing the fault current capacity. We know where we get the data from. And I just want to illustrate keep making this point that we ought to have everybody use the same rules, because otherwise you can't compare designs from different suppliers. And let's give a specific example of that. So basic cable data. This is a cable design from my company. Here's its basic mechanical data. Notice the cross-sectional area that we needed is right here. And then here's its published electrical data. Short circuit capacity, 146.4 K squared seconds. And then this cable gives the basic assumptions. The initial cable temperature 40 C, the final is 210, and the duration is 0.5. So it's not actually stated, but I do know that this supplier, which is my company, uses IEEE 738 methodology. So per the data sheet, the capacity is that 146.4, initial temperature, final temperature, the duration, and the methodology. If we change those assumptions and we use that 20 degrees C figure, and we change the final temperature to apply to the coolest component, then you get a new rating of 189.5 K squared second. So you've increased the apparent fault current capacity by 29% just by changing your assumptions. Cable itself hasn't changed. It's, in my opinion, it's a way of cheating, the way I put it. That's my assessment of it. And by the way, I don't take this for granted really, because there are some suppliers who will claim that they have a proprietary method for calculating fault current. And oh, it's just totally a coincidence that they get higher fault current values than everybody else. Yeah, right. So hopefully you understand why it's essential to have all suppliers use the same key assumptions and methodology. And in my opinion, they all should be shown on the cable data sheet. So even my own company, we should add that the IEEE method is used and that we're applying it to the hottest part of the cable. So to give you a qualitative overview of cable designs that are used today, you have center tube types, plain center tube construction where it's just a stainless steel tube with wires stranded around it, always have low fault current capacity. When you have center tube design with aluminum, whether it's cladding or put into a pipe, you do get up into the realm of medium fault current capacities. Aluminum pipe type designs, they tend to be medium to high. And then stranded stainless steel loose tube designs, also medium to high. So these cables are good when you're trying to keep diameter down. But when your fault current goes up, you really need to look at these design types. So now, some of you may be working on a project to replace a conventional shield wire, such as a 3/8 inch EHS or a 7 number 8. Want to replace one of those cables with OPGW, and it could be any other steel or ACS cable. And in that situation, you may wonder why you can't just say, please give me an OPGW design with a fault current capacity that's equivalent to whatever it is. And there are two reasons that this is not really a good idea. Reason number one, there's no precision to that. So you can't go to the Southwire Overhead Conductor Manual, flip to the pages for steel and ACS cables, and find published fault current capacities. You don't find that anywhere. The published data for the AC resistance is only up to 75 degrees C, and it actually shows a nonlinear increase. So something else is going on there. And more importantly, what upper temperature limit would you use, right? You don't have an optical unit or AY wire to worry about. So you can go higher than 210. But to understand the main point here is you have nothing to go to that says these are the fault current capacities of these cables. See, for example, here's ACS cable data from a leading ACS cable supplier, in this case, Introl, who's a very good ACS cable supplier. These are standard 7 number whatever configurations. You see you got your diameter, you got your breaking strength, you got your weight per foot, you got your cross-sectional area, and you've even got resistance, but oh, it's only DC resistance. And the big point is that there's no column over here that says fault current capacity. And if you think that, well, it's maybe that's just Introl, what about the other suppliers? Well, I've looked. You can go look too. You won't find fault current capacity column on anybody's data sheets. And then if you go look at the steel cable suppliers, you don't even get the DC resistance column. They don't even provide that. So, that's a problem. But there's another reason is that even if you go ahead, use the available data that you can find, it's not complete, but use it as best you can. And then you can debate what that final temperature limit should be, but you can also come up with a range, kind of on the conservative side, we could use this, and on the high side, we could use that. So we can roughly estimate what those capacities could be. And I'll show you this in a minute, but what I'm going to tell you now is we're going to find that the capacities are too low for today's power grid. And at first that may seem really surprising to you, but if you think about it a little bit further, it's not really that surprising because many of those cables were adopted on the order of 100 years ago, literally 100 years ago in the 20s, 1920s that is, when the demand on our power grid was much, much lower than it is today. So it's really no surprise that we find a mismatch. But nevertheless, let's do what I just said. Let's use what data we can find and rough it out. And here's what we'll find. So steel cables, 3/8 inch, if we allow, so I've made some assumptions about the AC resistance. And if we allow the final temperature to go up to 350 degrees C, 662 degrees F, we would get a fault current capacity of 9.7. Now, 350, no problem for the cable. And in fact, you can make an argument that you could go to 1000 degrees C, maybe even higher. No problem for the cable. Could have problems with the hardware, so could be other issues. But for the sake of this analysis, let's just use these two values. And you see that the average of them is 13. But recall that I said before, we typically see requirements in the range of 50 to 150. So this is way below the typical range that we see. 1/2 inch, you get a different value. 5/8 of an inch, you get different values. You could see that you've at least creeped into the middle of this range. For ACS cables, 7 number 8 is probably the most common. By the way, 3/8 inch and 7 number 8's got the exclamation point just because they're so commonly used. So 7 number 8, 350 C, excuse me, 27. Now, for 7 number whatever, you wouldn't want to carry it to 1000 degrees C. Why? The steel would be okay, but the aluminum cladding could be adversely affected. So I think 645 probably about the best, the highest you might want to go. And even then, that's not considering any issues that you might have with hardware. So 25.5. So an average 21. Wow. Oh, excuse me. Should have been looking at 7 number 8. 33. Still below our typical range. 7 number 7, you're right at the ragged edge. Don't see a lot of 7 number 7, a little bit of 7 number 6 and 7 number 5, and you see that you're still kind of in the mid range here, not on the high end of this range for sure. So in the 1920s, what I conclude is that friends don't let friends use 3/8 inch HS or EHS or 7 number 8, at least not for shield wire or ground wire. You know, you want to use it for guy wire, have at it. But for shield wire and ground wire, no way. Friends do help friends calculate the actual required fault current capacity and then proceed accordingly, shall we say. So we're going to conclude now with some, what can you do in a problem situation? So let's say that you've done all of this analysis that I've recommended, and you've come up with a very high fault current value. And what does that mean? Well, that's debatable, but let's, for purposes of today, say something over 200 K squared. What can you do? Well, you got 5 options. The first one is to just suck it up, right? And me as an OPGW supplier, I'm going to like that because remember what I said before, higher rating means more material. Well, that also means more money. Yay! So the OPGW suppliers like this. Next up, well, you could just live with the lower cable rating. Maybe you're already using a cable that's say 100K squared. You could do that. Again, it's higher risk, but you can make a financial case that makes sense long term. Plus, you can factor in that fault current drops off exponentially with distance. What that means is if you have fault current right at the substation, 200 K squared seconds, 1 to 2 miles away, it's going to be a lot lower. 80% is kind of typical. So if it was 200 there, it's going to be 20 within a couple of miles. The reason for that is energy gets dissipated at grounds along the way, right? Every structure along the way. Plus, the heat transformation in the cable is dissipating some of the energy and causing the current to drop. You can work with system planning to estimate the drop off. That would be specific. This is just to illustrate the concept. So let's keep going. You got three more options. Number 3, you could use 2 OPGW designs. You could have a high capacity cable for those first 1 to 2 miles, and then you can transition to one with less. So use a bigger cable for this first segment, and then transition to a smaller cable to go cross country and continue the line. By the way, are y'all still hearing me? Alexis?
Yes.
Okay, I'm concerned because I'm getting light flickering, and I now notice it's dark outside. Apparently there's a thunderstorm going by my house. Okay, so I should also mention that in that condition, or if a fault current did happen and you chose to just use a smaller cable and take the risk, the cable's not going to burn down for 1 to 2 miles. The cable is going to tend to burn down or be significantly damaged for 1 to 2 spans. So backing up that concept of using taking a calculated risk. But anyway, this using a high capacity cable and then switching to a low capacity cable, it's a good solution, but it does complicate your design and logistics, right? Because you got 2 cable designs. I got to design this cable, and I got to do sag and tension calculations, and I got to source the hardware for the big cable, and then I got to repeat all of that work for the smaller cable. So, I mean, maybe more design work means job security. Maybe the purchasing people like more work too. I don't know. That's kind of up to you and your utility. But basically, I can say that it does complicate the design and the logistics of your project, but it does work. Solution number 4, if you've got an H frame or any other tower design with 2 shield wire positions, you can share the load. What that looks like is you've got a primary OPGW and you've got this secondary cable that's there. The secondary cable could be an OPGW, or it could be some other conventional ground wire or shield wire. In any case, the fault current is going to divide between the 2 cables. That's a relatively simple calculation, resistance in parallel. It's going to divide based upon the relative resistance of the 2 cables. System planning, once again, they can help estimate that. As I say, the secondary cable could be another OPGW. I, as an OPGW supplier, like that a lot. Or you could use a conventional cable. If it's a conventional cable, I would urge you to consider a 19-strand construction. So that the fault current capacity of this second cable and it would be significantly higher. And the flip side of that is that its resistance would be significantly lower so that you would get better sharing of that load. 19-strand construction, in my opinion, would be better in today's environment than the traditional 7-strand cables that have commonly been used. So sharing the load. And your last solution, and I don't like this one. I'm going to preface this with I don't like it. I can't explain exactly why. I've seen some utilities. I did have a thought this morning, but it hasn't fully come borne fruit in my mind. But I'm going to talk about it because I see some utilities do it, and that's break the circuit just outside the substation. So normally your OPGW would come in and then it would continue from the last structure outside the substation. Then it would go in, typically a slack span, into a takeoff structure. And then from there, it would go down to a splice enclosure. And then from the splice enclosure, you might have a duct cable to go into a control house, something like that. There are different variations of this, but the basic concept. So to understand the concept of this, what you do is you take away that last span of OPGW. You could replace it with an ADSS. That's what I commonly see done by utilities that are using this concept. The AC, for purposes of this, I've shown the ADSS in a more traditional ADSS location, but the ADSS really could come where the shield wire is if you wanted to do that. Plan accordingly for the sag and tension differences between the ADSS and the phase conductors, but you could do that. Or you could go underground. And if you went underground, you could either go to the take-up structure again, or you could just go ahead and carry it all the way into the control house. So that's up to you. This solution does require that you add a splice enclosure where you otherwise wouldn't have had one. That does add some cost, but it's manageable. It also adds some splice loss, but in today's fusion splicers, the splice loss typically is going to be less than 0.01 dB. So not really a big factor. So anyway, it is a solution that's being done. As I say, I don't really care for it. And I'm just on the cusp of being able to explain why, but I got to keep going because we're really out of time. So one closing thing, and then we'll close out. So remember, I said the system planning department is going to need some help from you. Throughout this presentation, several times I've said you need some help from them, but there is something that they need from you, and I'm assuming that you're the one who's working with the OPGW supplier, and that is detailed electrical data. So to set up those models I referred to for calculating the fault current, they need good data. AC resistance, typically at least 2 temperatures. They need something called geometric mean radius, which is its own conversation actually, and a couple other things, inductive reactance and capacitive reactance. These are things that they need, and your OPGW supplier can provide it. So this is just a typical data extract, what we used before, but so a different supplier may present it in a different format, but it's the same information. And just to recap, now you know that you need to analyze your utility's fault currents and expected clearing times. You need to determine what current and clearing times you will use. You need to consider what initial and final temperature is most appropriate for your operating area. You need to calculate your required fault current capacity based upon what you've done preceding this point. And then you need to require that all OPGW suppliers use the same methodology and assumptions when computing the fault current capacity of their cables. And that concludes today's webinar. Let's see, do we have questions? Let's see. How long does the OPGW take to cool? It's on the order of minutes to hours. That also will depend upon the environmental conditions that you're under. So, for example, when you go do a fault current test at a laboratory, under lab conditions, if air conditioned testing, a building on a not so hot day, a cable can cool down, on the order of 30 minutes to an hour. But a long time ago, I did a fault current test at a testing center that had an outdoor span, and we were doing it in the summer, like I think it was July or August. I don't remember which. And that darn cable took like 4 hours, nearly 4 hours before it cooled back. And when you're doing fault current testing, you usually do a number of strikes. I think it's like 10 that you have to do. And so that testing took forever there. But yeah, it's not, your recloser is on the order of seconds. Yeah, during the time of seconds, you don't get significant cooling. Let's see, in the Southwire equation, K will be a composite value of the different materials. How do you assign T2 to any material? Yeah, good question. What you're doing there is treating the cable as a composite. And arguably that's not correct, but it's what's commonly done. And so how do you design T2? What you could do is, this thought just occurred to me, is you could do the equation separately based upon materials. So you could do the aluminum alloy wires, calculate them, do the aluminum clad steel wires, and then do the optical unit. And then you could treat that as that same resistance division formula that I alluded to earlier in the presentation. And then you could put everything back together. In theory, that would be a more accurate calculation, but nobody does that. And the reason is because of the fact that it is more complicated. And that the second reason is that you don't have the hard data on your optical unit. So you'd have to go out as a separate entity. You'd have to go out and do that separately, do some testing or something, or do some math to figure out how you would model that exactly. So what everybody, all the cable suppliers that I know of, and I've worked for 3, they're treating the cable as a composite and then applying the T2 to the overall cable. And then what you see when you go do testing is that method works. And it gives you a little, but not a lot of a margin for error. So that is treating it as a composite like that. When you actually go test it, your cables tend to conform to what you calculated. So if you said it was 100 k² seconds, it would rise the temperature to 210. When you actually go do the test, you might get 200 or 205, but you don't get 220. And in fact, you don't want that because that would be considered a testing failure. Hope that makes sense. So, okay. 3LG does not have ground current, so why would we use it to calculate the OPGW current? Why not use the worst case ground fault current, 1LG, 3 line to ground does not have ground current. So why would we use it to calculate the OPGW current? Why not use the worst case ground fault current for 1 line or 2 line? Typically 2 line to ground is slightly higher than 1 line to ground. I'm okay with that. I mean, I'm okay with that. I mean, my understanding is 3 line to ground does not have ground current. I disagree with that. If you're saying that 3 line to ground doesn't have current on the ground wire, yeah, okay, maybe. I don't know that to be the case because I would think that the current surge would still give an induced voltage and current on the ground wire. Anyway, as I presented it, it's my understanding that the 3-phase current gives you your highest value and the single-phase current gives you your lowest. And as you say here, the 2 line to ground would be somewhere in between the two. But I'm back to the basic concept. If you've determined that 3-line to ground does not have significant current on the OPGW or in the shield wire position, you could use whatever current you think it is, and that's what you would give your supplier, or that's what you would use to calculate the required current. And then from there, that's what you would give the supplier to rate a cable to. I stand by that methodology. Monty Tillmanen, hi Monty, by the way. The XR ratio might be an issue was at BPA. I don't understand the comment, so can you elaborate? Tufik, I believe duration should not exceed 0.5 because it will violate the thermal balance assumption of the heat of the equation. True. No, I disagree. Uh, uh, Obviously, the longer you make the duration, you are undercutting some of the assumptions of the thermal balance of that equation. But I don't think that it's a hard line at 0.5. I think it's more like, on the order of 1 second or maybe beyond that. Excuse me. But um, but as a practical matter, I've never seen expected clearing time exceed half a second. So I've never seen a need to use more than half a second. A high duration value improves current level capacity and can also be misleading. Does it? Like, I don't know. I'd have to think about that more, Tufik. Hi, by the way. I'm like, if I had the current and I'm saying that I applied it at let's say I want the current to be 100 K squared seconds. And then to keep the math super easy, I say the duration is a second. Well, then I'm saying my current would be 10. 10, because 10 squared is 100 times 1 is still 100. And that was the rating I wanted. If I'm saying no, it would be a half a second, then it would be, I need x squared times 0.5 to equal 100. And what's that work out to? X, I need this 100 x squared times, so I need 100 divided by 0.5, and then I need the square root of that. Now my current is 14.1. So I think, so now because I shortened the time, yeah, of course, the current goes up as I shorten the time. So high duration value improves current level capacity. So I actually think that this example shows the opposite, that if you let the duration go longer, it could it makes your apparent capacity go down. I will point out though that what I've observed is that when you shorten the duration in laboratory testing, because 99% of the time, well, maybe not that high, 90% of the time when you go to a lab, a customer has based their requirement on half a second. There's a notable exception, and that's AEP. They use a quarter of a second, and that's based upon their expected clearing time. And in their case, what I observed was